Welcome to the Machines and Molecules podcast. I'm Ingmar, your host. Machines and Molecules hosts guests that have backgrounds in biotechnology, biochemistry, and machine learning. And our guest today is Martin Steinegger, who is an assistant professor in the biology department in Seoul National University. And Martin contributed to many important tools in bioinformatics and or machine learning. Namely, he was one of the authors of AlphaFold 2, which made a lot of wind even in mainstream media for predicting folds of proteins from sequences. He is also the main contributor of the MMseqs 2 package, which is used in the largest protein databases in the world for clustering purposes, for example. I'm very happy to have you, Martin. How are you?
Oh, yeah. Thank you so much for having me on the podcast and for the nice introduction. I'm good. How are you?
I'm also good. Slept well. Just came from Hamburg back to Berlin. But yeah, it's a nice day and I'm right before vacation in Greece. So I'm feeling good. So I think one of the main things that I would be interested in is how do you productize research code? Because what I have seen you do very often is write tools and publish them that can be reused over and over and over again. Whereas in my research career, I tended to write something for a paper and then hope to write it in a general way so that I can reuse it. But very often it is copy and pasting of the code, adapting it, and then it's nothing that is easy to reuse. So what do you find important for productizing this kind of software so that it can be reused?
I think about that a lot. For me, developing something that lasts is very important. So for me, software is like the output is the method that will be used and can be used and reused. And the results are important, right? To make clear that the method has impact. But like at the end, it's great to see people actually using the software. And a lot of work that goes into developing this is really about thinking about how to interface. Like what is an easy way to use your tools, right? So how complicated can it be? It should not be complicated. It can be only one command. It has to have one input. It has to have one output, and that output should be intuitive when you get it out. So like the people just look at it and don't have to read through manuals really, really long. The tool cannot crash, right? You should not have something that crashes. It's very uncomfortable for users to figure that out. And then like another week of work might be gone. So you have a lot of times where you have maintenance. You read what users' problems are and you fix it. So for us, this published methods are really never ending work in some way because we always communicate with the community and try to make it better. And trying to not break it too much or change it too much so that pipelines don't break, but at the same time fix the bugs and improve the software. So it really is a good, pleasant user experience when doing it. And this is really a lot of engineering. And I understand in research, often we do not have the time to do that, right? And we often are having this one paper, get it out, and then we work on the next story because that's where we got our funding from.
Yeah.
But so that we mean that for us, an investment in the method is a lot of investment. So we have to be sure that when we build something that is meaningful and will be also used in general enough for a big enough community so that the effort is justified.
Yeah, what you describe is very software engineering, very company-like. Have you been in a company before that? Or did you just say, okay, I want this and I got to learn this even though I stay in academia and have always been in academia? I don't know. Have you been in a company before?
Yeah, before going actually to university, I was in a consulting company. I was working at Accenture as an IT consultant for a few years. They're mostly in the testing part. I don't know if that really influenced it. I always knew I wanted to build tools and software that is used even before going to the IT consulting company. Maybe the company time helped to just somehow focus and be maybe have some tools how to ensure software quality a bit better. But for me, it was always important that I somehow build something that people can use. I always thought when you spend 3 years on a paper or something, and you work on this really, really hard, and then you see very little usage of. Often bioinformatics is software, right? And you see very little people using it. I didn't want to go in that and in this direction. So I wanted people to enjoy using the software.
When you say in testing at Accenture, this was software testing also.
Yes, there was technical testing and also security testing. So technical testing meaning load testing. You have websites that have to have certain KPIs on performance, and so you need to check that. And so there's a software testing team, which is actually very technical work. It's writing code and so on to generate load onto the website, then monitor the website at the same time, see if it goes down, if it fulfills the criteria, and so on.
Yeah, and this is extremely useful for productizing, just to test all the time, right? Especially when you say we're trying not to break the pipelines but fix the bugs. It's impossible without testing, I guess.
Yes, we learned regression tests are very important. So for a colleague, Milot Medita, he actually, even though I'm coming from testing, he pushed me into the idea, like, why don't we do more regression testing? And I always know that's the right thing to do, but in research you move fast, and so you thought that's just slowing you down. But in hindsight, every software that we develop has a regression test behind. So whenever we commit something, it tells us if things break or not, and that's really valuable because you more often break things that you don't expect.
Yeah. And regression test in the sense of, I had a bug once, I didn't have a test for it, so now I introduce a test for it so that it doesn't happen again. Is that the kind of regression test you're talking about?
That would be perfect. No, our tests are more like the figures that we produce in the paper normally produce some kind of like rock values because some position, sensitivity, or certain speed. So our regression values are checking, like running a small version of these benchmarks and make sure that neither of these metrics really degrade in any way. But it doesn't guarantee that if you have some like user interface bug that you have fixed once and then returned it back to the old state somewhere, that this doesn't reoccur. But for important use cases, we make sure that we have a regression suite that somehow tests these these cases.
So in the sense of you're running a small, let's say it's a machine learning tool, you run it on a small data set and check that the outputs are what you would expect. That's it. Okay, understood. Maybe can you give an overview of the tools you have developed to people from machine learning that know nothing about biology, and so explain a bit also why this is important.
Yeah, let's explain MMseqs 2, which was the first big tool that I've worked on during my PhD. You can break it down to the idea of like document finding in computer science somehow. So you have millions of documents. Each document would be one protein. So there's a protein alignment tool, but let's just consider these proteins are documents. So you have a query phrase from a document, and you want to search all the documents where this phrase occurs. So now replace all of these documents with proteins. So proteins have amino acids. So words can be just single amino acids. And so you want to find like contiguous amino acids making up like a sub-sentence somewhere in your big database of proteins. And this is very important because it tells you something about the evolution of a protein. Like, because you find, for example, you take a human protein and you search it and you can find it somehow in bacteria. What does that tell us? That tells us somehow that there is somewhere a common ancestor between bacteria and humans that also had that protein in the past. And maybe that protein in bacteria might even have a very similar function to the one in humans. So you can even make functional assumptions. So we use these homology searches a lot in bioinformatics as a first guess of an unknown protein. What does it do, for example? And or building up these evolutionary trajectories, like saying, I found it in human, I found it in chimpanzees, and I might find it as well in this organisms, like understanding where does it come from, at what point of time did this protein exist. So it's like really one of the most fundamental tasks in bioinformatics to do these kind of sequence searches. So that's what MMseqs did. We extended MMseqs then later to do clustering. Clustering, very similar idea. You could see clustering as sequence search first, and then you group everything that is similar enough into groups. The problem with clustering was always that it's quite slow because you have to search all proteins in the database against all the other proteins in the database, which means you do n square comparisons. That's quite heavy. For databases that have hundreds of millions of proteins, that would take many years to finish. So we proposed an algorithm called linclust, which can reduce this problem to a linear time of comparison. So now instead of like a million times a million, you just have a million times a constant. And that is pretty doable computational. And that helped a lot to scale up a lot of the analysis to billions of protein sequences and compare them all across the tree of life and understand how they function. We later then transitioned to protein structures with like AlphaFold and having access to high quality predicted structures. There was really a need for fast solutions to search these structures. So similar to protein searches, you can now do the same thing, but in a structural space. So we extended MMseqs to work on structures by finding a way how to turn a protein structure, which is a three-dimensional object, into a string, which would be similar to an amino acid string that you have done before. Then you can use the same software again to do these kind of searches. And we worked on clustering of structures, which seems then also a logical step, right? Like now, how can you cluster that? So you can, again, use solutions from the past to use them now with the new kind of data type. So it's quite nice that you build these tools that are somehow becoming very general and you can then reuse the ideas in new domains somehow.
Yeah, that's the good part about building software so that it lasts and is stable and can be recombined even. Can you explain why people would go to structure? What does it have to say about the protein to have the structure, and why would you need it exactly?
Yeah, that's a good question. Before there was structural prediction, I always thought structures is not so useful. And now that we have all of these structures, I think, they're very useful. So I changed my mind as well. I was always like, hey, you can actually predict everything just based on the pure amino acids that will probably, because they should also encode the structure, right? So the amino acids, the protein string is the base for the structure. So why can't you do all the computation just on the amino acids? But I realized with structures, like a really easy example is, again, homology search. So you search proteins and you take this human protein and you find it in bacteria that I have mentioned. You can now align them. Many amino acids have already changed between human and bacteria. So you don't see the similarity very clearly just by the pure amino acids. But if you look structurally, visually with your eye, you can see that they are folding into the same three-dimensional object, and this three-dimensional object lie really nicely over each other. And I think for many people to trust these hits that are like search hits that are really far out in evolutionary time, structure helps a lot because you can actually now see it. You can see that, this actually has this loop. It has the same enzymatic site. I assume it probably has the same function.
Yeah. So would you say it's one of the aspects of structure being useful is the trust that it generates with people? Or is it also to be able to compare something that looks completely dissimilar, just looking at the amino acid sequence, but then when you go to structure, suddenly it's similar?
I think both. Like in the past, we had like many hits where we just didn't really know, like from in these similarity searches, you get some kind of score that tells you how similar it is. That score is then so at these borderlines, right? You kind of think it could be, I don't really know. And there really the structure helps. You get new confidence and you can make stronger statements because you actually see that the things are similar. And you can also put that in your paper and you can explain that in better ways. And the other thing is the resolution. Yes, we can now compare evolutionary distances that we couldn't before. We can just find things that are much further out than before. And both of these aspects are important. I don't know which one is more important than the other, but it's just two new avenues that we have now.
Yeah, understood. So I'm going through the same trajectory, I would say. I was like, okay, why do we need structure? I can do everything from the amino acid sequence. So in our company, we tended to focus on amino acid sequence in the beginning a lot. When would you... So I think part of this actually is productizing, because it's so easy to productize something that you can do from the sequence alone. And you can do an end-to-end optimization from sequence directly to, let's say, I don't know, stability of a protein or solubility of a protein with a pure regression model that takes in a sequence and spits out a number, and that's kind of it. I think the downside to structure to me often was, well, people like to look at it and we can't productize that. Like, you need human intuition. So when would you say, does it make sense to go for a pure statistical approach and when to go for a structure approach? Or maybe is there a good way to productize structure even when you want to do end-to-end?
I mean, you can see structure as an input to your statistical model, right? It will give you some more informed guesses that you can do. So if you think about the structure, and in the structure, some amino acids are in contact that are not really not in close proximity in amino acid range, that information is very valuable for mutation predictions, right? So if you want to know, can I mutate a certain position of a protein, or will it fall apart if I do so? It's important to know what it is interacting with. And the structure is giving you this. So you can just add onto your sequence model now a statistical term that tells you pair interactions, right? So that is already quite straightforward. So I think I see structures as a way to supercharge analysis now. So you can just do these old analysis, but you can do them somehow a bit better because you have a bit more insights into this protein family and as well as into the structure of that fold. So I wouldn't really distinguish them from, like, if you should go statistical or structural. I think you should do both, and you should integrate both at the same time.
I mean, this is very possible for something like enzymes, which have a very rigid structure, but becomes more difficult, of course, with, I don't know, intrinsically disordered proteins. Then suddenly you're out of luck with respect to structure. We talked about structure now. You've been one of the contributors to AlphaFold. Maybe can you say a few words about how that collaboration came to be and what the decisive insights were in developing the tool?
Yeah, DeepMind reached out to me about a few months after the AlphaFold 1 CASP results were released. So they already did know that they did quite well in the CASP competition with the first model. So they reached out and asked for databases for protein sequences. So AlphaFold cannot fold a single sequence. It's alone. So it somehow needs something called a multiple sequence alignment. And these multiple sequence alignments are generated by taking a protein sequence and searching it against a database, finding these similars, what I have described before, and then just turning each similar into one line. You can imagine you have your protein, query protein on top, and then each line becomes one of these homologous proteins, and that you give to the neural network, and it can then predict the structure for you. So the quality of the predictions really in the past correlated really heavily with how much amino acid sequences you had for that respective protein you want to fold. So DeepMind knew that, and so they wanted me to help them with the sequence databases. The reason for that is I have worked a lot in metagenomics. Metagenomics is this field where you go outside into the wild and you take a piece of sample and you throw it into the sequencing machine, you get DNA out, and then you do something with it. Like, there's like thousands of bacteria in them, like viruses in them, and so on. And we wrote a program that can extract the protein sequences from these DNA reads. And we extracted them from quite diverse environments, meaning we had access to a big protein database, which is called the BFD. At that time, that was beyond the scale that was available in any kind of public resources, and freely downloadable and so on. So I helped the DeepMind team to take this metagenomic data and turning it into a database that becomes searchable with a method called HHBlitz. It's an HMM-based protein search method, very sensitive. And this became part of the inference stage of the AlphaFold system. So whenever somebody uses the AlphaFold prediction, and it will do a search against big databases like UniProt, but also one search against this BFD, which is this big metagenomic collection, combines all of these hits and gives it to the model to predict the structure.
Okay, interesting. Maybe let's change gears a bit. I saw you post something about coming from the German so-called Hauptschule, which is one form of high school in Germany, which was introduced back in the 50s, I guess. I'm not sure about the history, but it was basically there for people that would go into being craftsmen later on, carpenters or whatever. And you went on to, after that, study computer science, do a PhD, and you're now an assistant professor at university. And just to give context to non-Germans, which is most of our audience, in Germany, typically, when you start in one school form, you stay in that social class and you don't move up, because Germany is really good in keeping people where they are, socially speaking. So I was quite amazed by the grit that that you must have shown in doing this journey, because it's not rags to riches in Germany for sure. So yeah, maybe can you tell us from your perspective what kind of mindset you had, at what point maybe did something trigger the mindset, or just give us a bit of background on that.
How much time do we have?
I think we can go. So if you have time, I have time.
Okay. This is really close to my heart. This is really a point that I discuss a lot with people in Germany. I'm obviously now surrounded by people that are mostly going through gymnasium, just saying this is the opposite one, that is the highest path where you then can enter university. And I barely meet I think I have never met anybody from Hauptschule so far. So it's really not really the case that you have that. So how did it get to this? So when I started with elementary school, my teachers didn't think I'm very intelligent. The reason for that is I grew up in a small Bavarian town. I'm dyslexic, and they didn't really understand what dyslexia is. And so they just know, that person doesn't understand how to write sentences. And so there must be some kind of thing wrong in his brain, and it doesn't really work. So I went to a special education school, actually, for some time. And that was awesome. That was a great school. People were really friendly. It was actually really a good school. So I think I was actually happy that I transitioned from this elementary school to this other school. It was a much friendlier and more educative place. It felt really peaceful. Then I went from that school, because I was very good in that school, I could go to Realschule, which is the middle path of the German schooling system. But again, a German teacher realized that I'm not good in writing German text, and ended up saying that, this person doesn't belong here. And then I had to go to Hauptschule. So I finished my education in this Hauptschule path, which doesn't really give me access to anything effectively. I knew already very early on in my life that I like computers. I was doing things very early on to get games running on computers where you had to, like, in this DOS interface, like, change the RAM settings that you have enough RAM to get that game into booting and so on. So I knew I wanted that. And in Germany, we have these job centers. So in job centers in Germany, they tell you what job can you do with the educational level that you have. So I'm coming from Hauptschule, going to the job center, talking to the person, saying, I love computers, I want to work in computers. And the person says, yeah, that's not going to happen with that education. You might be able to sell a computer in a store if you want to, but you will not be able to work on a computer. That was pretty much that statement. Okay. My father at that time, my father is from Austria, and in Austria they have a two system, and this is one is Hauptschule and Gymnasium. So Hauptschule is automatically on a higher level because you're not you're even the lowest, but you're just one step down. And so you can enter with Hauptschule degrees some technical school, which I then did for electronics. So I went to some school for electronics. I learned how to build amplifiers, how to solder things, how really the electronics works behind computers. And then, going to the civil service, which we had to do in Germany at that time. I still had to do my military as well, which I did in a civil service setting, where I worked in the IT support. I thought IT support is awesome. I wanted to work in IT support, and that was actually a good idea. So, but then I saw there's another school which is for business informatics, which I can also access now because I have this technical degree from Austria. So I went to this school, which was a 2-year kind of professional school, where I learned about more coding and also about the business sides a little bit. And then I joined the consulting company and then went to the university. So my way isn't really very straight. I just always knew I wanted to do something with computers. That was my path. And I was like, I have to go forward until I find the point where I can do things on computers that I'm happy with. Even IT support would have been okay for me, I think. But I saw more opportunities, so I moved forward.
What made you want to progress to what's perceived as higher and higher education?
Yeah, that's also interesting. I mean, I was at that consulting company, and so that was before I joined the university. And I was surrounded by people that go to university, and they told me, you should go to university. And I thought, nah, what will I learn there? I'm already in a consulting company. Everybody around me has university degrees, and I can do the things that they can do. So what will university teach me? I was a bit skeptical. But then I also realized that I was getting a bit bored of the work. It became repetitive and so on. And I wanted to do something new. And then the influences from these friends were like, okay, let's do that. So I actually talked to my parents at that time. I said, I want to go to university. And my father was actually not in favor of that. He said, why do you want to change? You have a stable job, you're running up in the career, you're getting more money and so on. You shouldn't really do that. But I decided anyway to do it. In hindsight, I really enjoyed that. I like to be in this research environment and having the opportunity to work on really interesting problems at the intersection between biology and computers. So I'm with each career step that I move forward, I got closer to what I enjoy the most somehow. And so going up that ladder from there felt really natural. I don't think I was really great in university, so my grades were not amazing, but I knew I loved the research. I was just doing research projects from the beginning, from the first semester onwards. I was just searching for opportunities to engage on research. And so the more I did the research itself, the more I realized the doing of the research is really what motivates me the most. So the excitement of working on something completely new. With each project, you have the chance to learn a new field and see what's happening there and see if you can make an impact there using your skills on computers, right? And that's really exciting.
Yeah. Yeah, I think I might misremember it, but I think there is a study even saying that PhD students are not the students who had the best grades, but rather one level down. Honestly, for me, it was always I've understood something. I don't need to know it all by heart because it's going to change anyway. So I don't care whether the grade is maybe one step down. So I think it was kind of the same for me. Yeah, that's very interesting. So being pushed by your interest and passion basically all the time, right? There was no, as far as I understand you, there was no single trigger event or something.
Yes, I didn't really have to. I didn't feel like I have to. Yeah, it was always the passion of like knowing that I want to do something with computers, want to learn more about it, want to see what I can learn more. I was for some time just buying all the books that I can about programming and so on early on, and like really just try to learn. And always like a new opportunity came. Oh, you can learn more about the topic you like. So why don't you do that? Until I reached, when I entered university, I didn't do classical computer science, but I did bioinformatics. So I picked biology and informatics. The reason for that is I thought at that stage, maybe I was arrogant, but I thought I have learned everything about computers already. I have done that so much now. Let's mix it up with a field that is totally new to me, like biology. I didn't know very much, nothing about chemistry, not much about biology. So let's just do that. And then I realized there are actually super interesting computational problems in bioinformatics that can be tackled through knowing a lot about computer science at the end, right? Or artificial intelligence by now.
Yeah. Also, one of my main motivations for the company that we've started, definitely to learn more about biology and realizing what a fascinating field, even just the sub part of proteins is. The theme of the podcast, Machines and Molecules, is that our guests bring a third M word. Have you thought of a third M word?
Yeah, I have two for you. So I played in a band for some time, and I had an artist name, and that artist name was Mad Marvelous. So you can go with Mad or Marvelous. I would prefer Marvelous probably. So I will go with the word Marvelous.
What did you play in the band?
I play the guitar. Yeah.
Okay. And what kind of band was it?
Everybody starts as a punk band because they don't know how to play the instruments well. So I guess we started off as a punk band and then developed into we called it new school rock and roll. I guess it was a mixture of later a bit of try to get some electronic influences in and just make a bit like progressive kind of rock. Like a progressive rock is also not the right term. That sounds more too technical. So something in between rock, punk, and influenced by electronics.
And how long did you play in the band? How long did the band exist?
That's quite some time. I tried to keep that up most of the time, even though I moved quite a lot through Germany. I always still kept the band. Maybe about 5-6 years, I think. I was in the band existed longer, so that they already started before me. So I was always the new person in the band. It was like 5 years, and it was quite busy as well because nearly every weekend or every other weekend we had like a show somewhere where we had to go.
Okay.
Yeah.
Okay. So you had so many shows even. That is nice. What was the band called?
It's called Chromatic Black.
Chromatic Black. Okay. Very nice. Martin, thank you for the very enjoyable chat. I think this will be very enjoyable to our audience as well, and hope to see you at a conference or in Seoul at some point. Thank you, and have a nice weekend.
Yeah, thank you so much. Please visit me in Seoul.
I will. Bye.
Okay. Bye bye.